So on the homework sheet, you might notice that there is, I think I mentioned this a little bit ago, that I did, this is years ago, I did these answers. And so I thought, well, I might as well just put them up there for now, since you guys might be able to benefit from them. So for example, today's answers I made available. I'll make them available as the time, after, whoops. Like after you're supposed to hand them in. So I guess also if you're behind on your homework, you could always use my answers to get your answers, I guess. But let's take a look at these and see if there are any questions. It's pretty straightforward though. You're doing the root test, which is like the ratio test, but you're doing an nth root instead of an nth or a ratio. But I think it's pretty straightforward. But are there questions about this? Is there anyone that needs to look at one of these in more detail? What do you think, Michael? So let's see. I hope I did it. Hold on a sec. Number 30, 30, 30, 30. That's the last one. Oh, arctan. Oh, we love arctangent. Well, okay, I do. Here it is. Yeah, so there it is. Is you're doing the limit of the nth root of this. And of course, you probably are fine with this stage, saying, yeah, you just get rid of the root. And so that's fine. But it's this limit that you're not sure about, right? So what is the limit as n approaches infinity of arctangent of n? Well, as we all know, the arctangent function looks like this. Here, I'll just do a quick sketch. So it looks like a tangent curve on its side. So that's what arctangent is. It looks like this. There we go. So that's arctan. And so as you get closer to infinity, this gets closer to pi over 2. So the limit as n approaches infinity or x approaches infinity of arctangent is pi over 2. Another way to do this if you're not sure, so like if you're on a test and you're panicking and you're like, oh, I know Dr. Noonan's going to have an arctangent. I don't know my arctangent. Is you could always take your calculator and say, okay, well, what's the arctangent of 1,000? So arctangent is second tangent, and then type in like 1 million, and you get 1.5707. You might not know that that's approximately pi over 2, but you can tell that that's bigger than 1. So since that's bigger than 1, this thing will diverge. So that's the key there, is you're doing that limit, and as long as that limit, bigger than 1, diverging, less than 1, converges. Because we're doing the absolute value. I left off the absolute value here because I knew arctangent was always positive for large values. In fact, it doesn't oscillate. All right, so that's it. Does that help, Michael? You clear it up? Okay, Daniel, what do you think? Which one, 29? What about it? It's right above it. It diverges. Oh, let's see, what happened up here? Oh, yeah. Oh, this one is, this one's a good one. Here. Okay, so just a sec. So how in the world do we do that one? You see, the big issue is when you get to this stage, right? Like, what do we do with that? So, anyway, let's talk about that. That's fascinating. Sorry, I'm trying to figure out what to do. Here we go. We'll do this. Ignore that. Yeah, so it's this limit, the limit as n approaches infinity of 1 plus, what was it again? Sorry. Here it is. Yeah, 1 plus 1 over n. That's it. 1 over n to the nth power. Sorry, that's kind of weird. Let me fix that so it doesn't look dumb. For some reason, I was thinking I was going to make a fraction. Okay, yeah, there it is. Now it looks even dumber. Oh, well, there it is. Yeah, so what's the limit as n approaches infinity of this thing? There's a variety of ways that you could do this if you didn't know. So this, by the way, the answer here is that this is E. This is related to compound interest formula. But anyway, if you didn't know that this was the case, what you could do is you could use logarithms to figure this out. And so if we really want to do this, you could do this. We could call this capital Y is going to be 1, the limit as n approaches infinity of this thing, 1 over n to the n. And then we'll do the natural log of y. which is going to be the limit as n approaches infinity of the natural log of 1 plus 1 over n to the nth power. So natural log of y, sorry about my mess here, is the limit as n approaches infinity of n times natural log of 1 plus 1 over n. Okay, so far so good. This is just rules of logarithms here. Move the n over here. Don't worry, it's going to make sense in a sec. And then we're going to do, let's see, this is the limit. I know this is way more than you bargained for, I realize. So let's see, how I want to do this. We'll do it like this. Natural log of 1 plus 1 over n over 1 over n. There we go. No, let's do it the other way. So there's two ways to do this. Let's see, we'll do it this way. N over 1 over 1 plus 1 over n. There we go. Okay, so now that we have it like this, either way you did that, you saw the other way I did it, you end up with the L'Hopital's rule indeterminate form. So this is infinity over infinity. The other one I had was 0 over 0. So you do derivatives. I don't know. This might be, either way, it's going to be a pain. So let's see if we can do our derivatives using L'Hopital's rule. You get limit as n approaches infinity of 1 over, let's see, this is going to be 1 over 1 plus 1 over n. Yeah, this may have been a bad choice. Yeah, I changed my mind. Yeah, let's change it. This is just ugly. Let's go the other way. Just a sec. So this will be natural log. I could do it, just there's more chain rules involved with the way that I had it there. Okay, so this is a L'Hopital's rule in indeterminate form because natural log of 1 is 0, 1 over n when n goes to infinity is 0. So 0 over 0, L'Hopital's rule, you do the derivatives. So now this should be a little easier. 1 plus 1 over n times the derivative of that is negative 1 over n squared all over negative 1 over n squared, and that is equal to 1. Hopefully you can see that this is going to cancel this, and then you do the limit as n approaches infinity of this, you get 1. So that's 1, but notice that's the natural log of my goal, and so the actual y is going to be e to the 1, and that's why this is e. So just an interesting little fact, if you didn't know it, is that the limit as n approaches infinity of that thing is e. Oh yeah, so that means I diverges? Yeah, I know. Daniel's like, I just wanted to know the answer. So here's the answer is that you get this limit is e greater than 1, diverge. So that's a little bit technical, not to worry. On the quiz, it's much simpler, like, let me see, where are the other two? I think it's like the other two. Yeah, that one, or better yet, the one before it. Oh yeah, that one. That one's beautiful, isn't it? Yeah, it's more like that on the quiz and on the test next week, or 2 weeks from now, 2 weeks. So anything else? I guess we pretty much did them all. We got them all. So let's do this. Do a quiz, be happy about it, and then we'll move on from there. There's 2. There's a couple. There may be 3 there. I don't know. Here's 2. Here you go. There's some. Here, you want a few, don't you? That's 2. Let me give you one more just for fun. Here you go. There. Here, I'll just give you one. There's another. You want? There's 2. Good job. Let's see. Let's hope for the best here. Oh, I didn't give you one. Oh, I only gave you 2. I didn't even see you over there, Thomas. I'm sorry. Okay, so you have enough. You have enough. How about up here? Does everyone have enough? Amazing. Good distribution. I'll put it up on the screen for the 1 or 2 people who are not here. Let's see. Quiz root test. There it is. There's the first one. Oh, what's this? All right, hopefully you're coming down the home stretch with these two. Not all that complicated. Well, if it is complicated, then I don't know. Well, it looks like, yeah, this whole front row is done. So if you are done, feel free to send it over or make me walk. It's either way is fine. I didn't wear my Fitbit today, so I'm not going to get credit for walking around. Oh, you take your time, meditate. Look good? Yep. You sure? All right. Okay. Very philosophical view. All right. Does this look okay? Oh, I like your sweatshirt. Very nice. Guess I need to start getting some swag like that. What? Oh, I love it too. I was noticing that as well. But I'm always hesitant to comment on people's hair because I don't want to make them feel either, I don't know, bad. Like, I don't know. It looks good though. I need to do something, maybe not that extreme, but yeah, thank you. All right, we're coming down the home stretch. Very nice, good job. Uh-oh, did you break it? Wait, did you, what? I see, nice. Okay, front row's done. Okay, yeah, send that on over. Yeah, thank you. Thank you. Couple more. Meditating, very nice. Good job. Excellent. All right. Oh, you've got it boxed up? You just don't like it? Okay. Oh, you got something though. Oh, interesting. Oh, I like your method. Like, if you don't, it's good to try different things. All right, so I think I got them all now. Anyone holding out on me? All right, let's give it a go here. Um, see how I did. Hopefully, I did it right. Oh, there. Oh, come on. These staples need to be a little stronger. That's better. Okay, so first one, pretty straightforward. This one was the easy one, wasn't it? The main thing about this one that you might have noticed or not noticed, and if you didn't, I'm probably going to just squint when I look at your paper and be fine with it, is that if you do the absolute value of this, now of course the -1 goes away, but notice the denominator, you have that -2 down there, that in the limit, that ends up becoming -1/2, but you do the absolute value and you get +1/2. So there's that little tidbit, but the important thing is it does converge because the limit is 1/2. So this one was a little bit harder. Because you might not have known about this, what this limit was or how to do it. I think we've had a few of these already, but here's the limit. Get rid of the in, and you get this. I guess I just have the answer here. It's infinity. But if you didn't know, you could do something like this. That this is going to be, think of the partial or the terms. So 3 over 1, and then 3 times 3 over 2 times 1, 3 times, 2 times 2 times 2, 3 times 3 times 3 over 3 times 3 times 3, 3 times 3 times 3, 3 over 4 times 4 times 4. So the important thing, though, is that these things get big. Oh, you could use L'Hopital's rule. Yeah, I just realized you could use L'Hopital's rule. Never mind. L'Hopital's rule would work with this. A lot easier than trying to guess. So L'Hopital's rule, I'll do it. L'Hopital's rule says you do the derivative of the top over the derivative of the bottom, and you get infinity over infinity again. So you do the derivative of the top over the derivative of the bottom. You probably see where this is going. Infinity over infinity, do L'Hopital's rule a third time. What could be better? Over that, this is infinity. So there you go. So there's L'Hopital's rule, triple L'Hopital. Okay, let's move on. We're going to be doing power series. If I don't know if the videos are available or not from the COVID, but I remember when I did this during COVID, I had like a monster truck rally going in the background, because power. Okay, well, anyway, maybe I'll try to dig that video out. I don't know if do you have the COVID videos on there? I think just a few of them. Yeah, I'll find it and point it to you. It's kind of funny if you're looking for some entertainment this weekend. But power series, what's a power series? It's something like this. Okay, so here's the difference. Up here at the top, that is a geometric series, right? Geometric series, you're familiar with this. It's got numbers. Well, it's got an R there, but if I told you what R was, you could tell me what that sum is. So for example, if I did this, here, we'll do this. Or R is equal to 1/2, 1/2 to the n, where n goes from 0 to infinity. You can add that up for me, can't you? You can. Take a minute, tell me what the sum is. Randomize. I keep sipping this thinking it'll taste better the next time, but it doesn't. I think I steeped it too long. Okay, so Michael H., you know what this sum is, don't you? The geometric series formula. I'll remind you, what's the first term? 1. So you do 1 over, and then 1, what is it? 1 minus? And what's the R? 1/2. Very good. Okay, so that's going to equal 2. Beautiful. Okay, so if you knew what the R was, you could do this. Here, let's just do one more just for fun. Let's do this one. N goes from 0 to infinity of, let's do 4/3 to the n, just to do another practice. Let's find another random person. So Hayden, do you think you can use the same formula for this one? Go ahead. Oh, just 4/3. The common ratio is 4/3, right? Yeah, I know, it's early. That's fine. Okay, so what do I get here? This is going to be negative 1/3. So this is equal to -3. That's interesting. Add up a bunch of positive numbers, we get a negative number? Wait a minute, something's wrong here. What's wrong? What is wrong? Oh, so there's a trick question, Hayden, sorry. Can I use the same formula? No, I can't, because here, the common ratio, this is a no. No, because the common ratio is bigger than 1. Anytime the common ratio is outside the range from -1 to +1, so this is it's a no. It diverges. So that's the key there. So here's the deal: is up top I have this thing, and you know the formula. The formula is this: 1 over 1 minus r, as long as r is between -1 and +1. So when r equals between -1 and +1. Now here's the cool thing about this, is we're going to be changing from r to x. And when you change to x, you think, oh, this is no longer just a formula for a sequence. It's now a function. You're used to functions, aren't you? You know about functions. And so this is now a function. We're going to call this f of x. F of x is this. And we can still use the same formula, though. Check this out. This is 1 over 1 minus x, as long as x is between -1 and 1. Whoops, I have a comma there. Just ignore the comma. Okay, so just think of this as the domain. As long as x is between -1 and 1, these two are exactly the same thing. I know you think it's unbelievable, so I actually graphed this. Let's see. Oh, it's still going. Wow. I've got another thing that I'm working on here. Maybe I should stop that so that there. There we go. Okay, so here's my graph. Okay, so up here. So this, oh wait, where is it? There it is. There it is. So this is the graph of 1 over 1 minus x between -1 and +1. It has this point here at 1. Of course, there's an asymptote, because if you put 1 minus 1 in the bottom, you do get this. So actually, I graphed it up to 0.9 just because I wanted to avoid that. Okay, down here, what I've done is I've graphed this, and I've graphed the sum. Here, I should write up here what I'm graphing so that you know what to look for. So I'm going to graph this, and I'm going to graph a partial sum. So the partial sum is this one: 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th. So I'm going to graph this and that thing. It doesn't look like, these don't look at all alike, do they? The one is a polynomial. It's a 6th degree polynomial. Nasty, isn't it? But check it out. When I graph the two of them on top of one another, here's what I get. Here, how do I do this? Here we go. There it is. There they are. Look at the green one. The green one is that x to the 6th. And then the orange one is the 1 over 1 minus x. Now, the reason why I did it this way is so that I could actually do this for, go up to x to the 10th, just to see what happens. And here's what the graph looks like when you get x to the 10th. Notice that the green curve is getting closer. Let's go all the way to x to the 20th. Let's go x to the 20th, and we get this. Look at that. They're almost on top of one another. They diverge down there and at the very ends. In fact, if I go to the x to the 1,000, let's just add up all of them all the way up to 1,000. Then they're basically on top of one another, except for, look, a little whoop, at the very end there. But that, you're getting close to -1, and so of course there's going to be a little bit of a problem down there. But look how close they are. That's what we mean when we say that this function and that series are the same function. So we're interested in these sorts of things. These sorts of things are called power series. A power series is just a series that has x in it. Just think of it that way. It's a series with x. So it turns a series into a function. Now, the reason why we're interested in this is because when you have functions that are represented as series, you sometimes can do things with them that you couldn't do when you had the function. Like certain integrals are much easier if you know the series. Yeah, we don't even write any of this down. But I just wanted to show you some of my favorite series. We'll go over this next week. But e to the x has this beautiful series representation. Sine and cosine are really beautiful as well. Same with the hyperbolics. And then, of course, how can I leave arctangent out of the mix here? We'll go over all of these. In fact, later today, if we have time, we'll have the arctangent series, and I'll show you where that comes from. Okay, so here is what a power series is. A power series is just a series that has x. It's pretty much it. So you have an x, and you have some numbers. So the c's are just constants or numbers, and that's it. That's what a power series is. So those are the coefficients. It's like a polynomial that goes on forever. So this polynomial just keeps going and going and going, and never ends. So that's what a series is. So this is why we've suffered for the past 3 weeks with series, is because we're coming back to functions, and we're going to do some calculus. That's the exciting part here. Okay, so let's see. We have to start simple, though. So where is my simple stuff here? We already know. Okay, so the most important series is this one. Wait, not that one. It's this one, that one. Okay. So here's my generic series, C0 plus C1x plus C2x squared, and so on. So if I say, let's make all of those constants equal to 1, you get this series, and that's going to be the most important of our series, at least for the time being. This power series, it actually has this as its function representation, because that is a geometric series. So these, as long as x is between 1 and -1. So that's a series, and that's the representation of that power series. Well, let's try another series. So that one is pretty obvious just from the fact that we know about geometric series. We're going to use that as a stepping stone to understand some other power series. But first, let's just take a look at, let's see. I can't see what's coming up. Oh, that's boring. Just a minute. This one. Let's take a look at this one. Yeah, well, no, let's do this one. This one first. So one of the questions that we're going to be asking ourselves is, for what values does a particular power series converge? Back here, this one we knew because we know the geometric series. We know the geometric series formula. But what about this one? What numbers does this series converge? Let me just write down the first few values of this series so that you understand what it's talking about. 0 factorial times x to the 0 is 1, plus 1 factorial times x to the first is just x, plus 2 factorial times x to the second is 2x squared, plus 6x cubed, plus 24x to the fourth. If you know your factorials, this is what you'd get. If you don't know them, you could use your calculator. I've run out of room, though. So that's what we're talking about, is that is the power series. So what values does this converge? Well, if you were doing this, so let's take this series. You would go through your flow chart, right? You have that flow chart. So ignore the x for a minute. The x is just like, think of it as a placeholder, like alpha or d or g or whatever. It's a number. So you'd go through your little flow chart. Is this geometric? No. Is this a p series? No. Can I use the integral test? Yeah. You go through the list, and you get down to the bottom. Those two at the bottom are going to be the most important for us, and that is the ratio test and the root test. Usually we're going to end up down there somewhere. So let's just cut to the end and do the ratio test for this. So we want to do the ratio test. So the ratio test says we're going to do the limit as n approaches infinity of this, n plus 1 factorial times x to the n plus 1 all over n factorial times x to the n. This isn't too bad, but see if you can simplify this, and then I'll show you how I simplify it. And then we will talk about what it means to have that absolute value there, and the limit, and the x. It all matters. All right, let's see. Here's what I would do to simplify this. Remember that n plus 1 factorial is just n plus 1 times n factorial. Okay, n plus 1 times n factorial. So the n factorials cancel. Okay, I'll do it like this. Over n factorial. And then there's an x in there somewhere. I ran out of room because of this thing. But anyway, so the x's, that's easy. Most of the x's cancel. You're left with just one x in the numerator. The n factorials cancel, and you're left with this. The limit as n approaches infinity of n plus 1 times x. Now, you could do this limit, but here's the thing is I'm interested in what values of x will make this converge. So essentially, instead of putting an equal sign there, I'm going to put less than 1. And then I'll ask you, can you think of any values of x that will make that statement true? Like at first glance, you might look at that and say, well, wait a minute, when I do the limit as n approaches infinity, this thing is going to blow up. This is going to be infinity. So this diverges. But there is one value of x that will make this not infinity. Do you know which one it is? Yeah, if x equals 0, that'll make this thing not blow up. It won't be infinity. And so this thing is only true only when x equals 0. So if x equals 0, then this converges. So what values of x does that series converge? Just when x equals 0. No matter what other number you put in here for x, this will be bigger than 1, won't it? It'll be infinity. So not very exciting, but that's the answer. What values does it converge? It converges only when x equals 0. Let's do a little bit more exciting one. This one's not very exciting to me because it's only true when x equals 0. The next one is more interesting, I think. So let's take a look at this. I want to know, when does that converge and when does it diverge? So the way I'm going to do this is generally the go-to test is going to be the ratio test. So this is a power series. It's got an x in it, right? So let's do the power series, the ratio test. The limit as n approaches infinity of the absolute value of, I'll do it carefully here. So take a look at that. See if you can simplify that. So this is going to take a little bit of effort here, but see if you can simplify that, and then we'll throw the inequality. We'll have a less than 1 here in a bit, but I'm going to simplify it first. So there's going to be a little bit of algebra in your futures, and just you're going to be okay. All right, let me see. Here's what I would do with this. It's probably similar to what you did. We're going to do the limit as n approaches infinity. Let's flip that bottom. So x minus 3 to the n plus 1 times n over x minus 3 to the n times n plus 1. So it's probably similar to what you did, I hope. And then you're going to cancel some stuff. So that equals the limit as n approaches infinity of x, x minus 3 to the n plus 1. Oh, no. I'm going to cancel, I'm going to cancel the x minus 3's. So let's pause for just a sec. Or no, I'll do one more thing. So you might have done this. Let me do one more thing. There. So I need to know the limit as n approaches infinity of this thing. And this I'm actually going to do before I introduce the whole 1. You know, like we're going to compare this to 1 eventually to figure out whether it is, let's see. So Karen, what's the limit as n approaches infinity of just this fraction here? Yeah, it's just 1, right? Because you have n over n plus 1, you know that that's going to be 1. So you can do the limit before you do this, the last bit here. I'll show you. In fact, it's usually better if you do the limit first. So this is going to equal this, that times 1. And now I want, so this will converge as long as that is less than 1. So here's what I'll do, is I'll do this, x minus 3 is less than 1. So you can do the algebra here, can't you? X minus 3 is less than 1. What does that mean? It means that x minus 3 is between 1 and negative 1. And then you can add 3 to, well, all 3 sides of that equation. But add 3 to everything, and you get that x is between 2 and 4. So let me back off, just see what we got here, see if that makes sense. Because we're not done with this, sadly. There's another piece. In fact, it's so sad because I'm going to have to switch over to Notability, which I should have started out to begin with. But I want to make sure that this stuff makes sense before we switch over. So the important thing, so this, we're going to do this multiple times today, at least in the 20 minutes we have left. The important thing is that you're going to set up the ratio test. Usually it's the ratio test. There will be certain situations where the root test makes more sense. Set up your ratio test, do all the simplification that you can, and then get down to something that looks like this, hopefully. And then you'll get an inequality, you'll get a range. So this tells me that that series up there, it will converge as long as x is between 2 and 4. So as long as x is between 2 and 4, you're going to converge. So that part hopefully makes sense. Yeah, Hayden?
So why can't x be 1 or 0?
Why not?
Yeah.
Okay, well, if x equals... Oh, you're asking about this inequality right here? And the 2 endpoints? That's the next thing that we have to deal with. So no, you're on the right track here, but I want to make sure that this part makes sense. We'll deal with the 1 and negative 1. Don't worry. Yeah, it is more complicated than at first it would seem. Like at first you think, oh, I just need to figure out what values of x will, make this thing less than 1. So here we have this is less than 1. That's between 2 and 4. But Hayden's concern is the correct concern, and that is what's going to happen when x equals 2. So yeah, that would correspond with negative 1. And when x equals 4. You see, the problem with x equals 2 and x equals 4 is that the limit would be equal to 1, not less than 1. And when the limit equals 1, the ratio test is inconclusive. We don't know. It could go either way. So this is the worst part of power series. This part actually is what we just did. I know it looks scary, but it's really not too bad. The worst part is that you have to keep going. So here's the deal is we've got that. And then we have to ask ourselves, what's going on when x equals 2, and what's going on when x equals 4. So here's how you would do that. So when x equals 2, you're going to write down the series. This is the original series, but you're going to change x to 2. So when you change x to 2, you get negative 1 to the n over n. We're going to do the same thing when x equals 4. Write down the original series. Here, maybe just in case you're wondering where that negative 1 came from. That negative 1 came from the fact that 2 minus 3 equals negative 1. And I'm going to do the same thing for x equals 4. 4 minus 3 is positive 1. So now we go back to this and we say, does this thing converge or diverge? Is it going to converge or does it diverge? Same thing with this one. Does this one converge or does it diverge? Take a minute, see if you can identify. Now it's just like what you did a couple of weeks ago. Actually, you probably could have done this one, well, last week for sure. So take a guess, or maybe it's not a guess, maybe you know. We'll do these one at a time. Braden, do you know about that first one, the one on the left? That's when x equals 2. Does that converge or diverge? So what test are you using? What kind of a series is that? You got a negative, positive, negative. What do we call that? Alternating. Yes, it's an alternating series. So Braden says it's alternating. I can use the alternating series test. So let's see. Ethan, do you remember the alternating series test? The alternating series test says, let's ignore the negative 1 part and ask, do the terms go to 0? Do the terms go to 0? 1 over n. Does that get smaller? It does, and it does go to 0. So remember the alternating series test. B is, and this is greater than 0, and b sub n is decreasing, and the limit as n approaches infinity. I was trying to avoid having to write all this stuff, is 0. And so this one actually does converge. Very good. So when x equals 2, that thing converges. So there's the two alternating series tests. You're going to be using the alternating series test quite a bit for these, as you might guess. On the other side, what kind of series is that? Let's find another volunteer. We got Caleb. Caleb, do you know what kind of series that is? It is a p-series. Now, if you aren't as quick as Caleb, let me just write this down so that you can see what it looks like. This is just 1 over n to the first power. That is because 1 to the n is 1, no matter what you put in there. So that is a p-series. Christian, what is the p for this p-series? Does that converge or diverge? Diverges. We also have a name for this. This is called the harmonic series. So this one does diverge. So diverges on that side, converges on this side. So the final answer is that this will converge. This converges as long as x is between 2 and 4, including the 2, but not including the 4. I know, so much to do. So you have to worry about your interval, and you have to worry about the endpoints. I know this feels quick, but we do need to do a couple more before we go. So, oh, come on. Oh, well. Let's do this again. So we did that one. Let's do the next one. Let's see, how's this one go? Oh, that is that one. Just a sec. Example 2, try this one. Here we go, this one. Okay, so we'll try this one. Or you could try it. And I'm going to put it on, you give this one a go while I move it over to Notability. So basically, you're going to set it up using the ratio test. That's your first move, is set up the ratio test, and then we'll go from there. Wow. Okay, finally got myself set up. Here's my thing, and here I'll write it down. So ratio test. Ratio test. n approaches infinity. All right, let's see who gets to do this. Carson wants to set it up, don't you? Carson, what do I do to set up this ratio test? What goes on top of this ratio? All right, very nice. What about on the bottom? Now, I noticed something about what you just did, and that is that you forgot about the -1. Why'd you do that? Yeah, it's an absolute value, so it doesn't matter. Yeah, so it's totally fine what Carson did, and that is that since we know that we're going to be doing an absolute value, -1 is not going to really matter. So you can leave the -1 out of it, saves you a little bit of effort when you get over here. Go ahead and simplify that. I'm going to do the same up here and see if we get the same thing. So after you get done simplifying, see if you have the same thing I have. I'm just going to rewrite mine to make it a little easier for the next volunteer. All right, who is it? Ryan. Ryan, what do you think of this limit? Can I do that limit? Yeah, just 1 times x. There's another way to do it. If you're worried about this n plus 1 to the 5th, I mean, we all know what n plus 1 to the 5th is. It's kind of a pain. Into the 5th times plus 5 into the 4th plus 10 into the 3rd goes on. You know what it is. But anyway, it's kind of a pain to think of that. Another way to do this, if you don't want to have to think in terms of n plus 1 to the 5th, is you could do this. N goes to infinity. And this trick works for a lot of these problems. There, just do that. Now you don't even have to worry about the 5th power because now what Ryan did was perfect, but this is just a limit as n approaches infinity of this is just 1 to the 5th. So either way you cut it, you get x. So we're almost there. We know that this has to be less than 1. So here, just to review, you do the ratio test. Whatever you get, hopefully will have an x in it, and you want that thing, whoops, I didn't mean to put that there. That thing should be less than 1. You're going to rewrite this as an interval. Usually you'll have some sort of interval. So 1 to -1. Now the most painful part, at least I always found this to be so painful, because we just did all of this work and it's all so beautiful. And yet we still have to go back and ask ourselves, what's happening when x equals -1? And what's happening when x equals +1? Ah, I just did all of that. Okay, well, let's do it. We'll do it quickly. Okay, so what's happening when x equals -1? And what's happening when x equals +1? So basically what you do is you take that series up there and rewrite it. When x equals -1, you have this sum. And when I'll zoom in so you can see it better in just a minute. -1 to the n times 1 over n to the 5th. Okay, there we go. So there are my two series, my two endpoints. Okay, well, let's see if we can make quick work of this. First of all, -1 to the n times -1 to the n is -1 squared to the n, which is just 1 to the n. So this thing is the same as this. I can't do much about this one on the right other than to get rid of that 1 there. Yeah, we'll just get rid of that. There. Okay, so let's deal with these individually. Lewis, you know about the one on the left here, don't you? That's got a special name, doesn't it? What kind of series is that? It is a P series. What's the P for that one? Yeah, so does that converge or diverge? Yes, p equals 5, which is greater than 1, which means this converges. Very nice. Now, how about this one? Let's get our next volunteer. Here we go. Thomas, do you know what that is? What kind of series is that? Alternating. And does this converge or diverge? Yeah, it converges. Actually, once you do this one, you're like, well, if this one converges, for sure that one will. But that one does converge as well. You can go through the motions if you need to. So what that tells me is that this converges on both endpoints. So that's going to be my interval of convergence. X can be anything between -1 and 1, including -1 and +1. So don't assume that it's not going to converge at the endpoints, because it sometimes does at both. Lots of work there. Wow. I think we have time for one more. So we'll, but I want to make sure that no one's losing their mind. I mean, or you might have already lost it. I don't know. Okay, let's do one more, and then we'll call it a day. Let's see, what's the last one that we get to do? Let's try to pick a good one. Ooh, I like these. Look at that, you got a little power guide there. Let me see. These are all so good. How about we do, let's do this one, because that one looks like the most confusing one. Yeah, that one looks good. Yeah, let's do this one down here. This x minus pi to the n over 3n factorial. The other ones are pretty easy. By the way, just a quick note. With this one, you probably would do better to use the root test, because you can see it kind of looks like the root test thing. But yeah, this one looks like fun. Oh, that one's good too. Okay, let's do this one though, I've already said. So the x minus pi. I'm going to move it over to Notability so I have more room. Done. Copy and delete. Just a sec. There it is. Beautiful. All right, so your first step, of course, is to write this as a limit. Hopefully you've got it sorted out. This one's a little bit hard because of this down here, this 3n factorial, whatever that means. Here's what I've got written if you want to see. Here, I'll zoom in a little bit more so you can see it better. So there's that. So notice that n became n plus 1, but it's in parentheses, so it's actually technically 3n plus 3. So then we're going to simplify that. I'll give you a minute. I'm going to do it as well up here, but I want to give you a chance to see if you can do it right. Okay, so what I did was I canceled all but one of the x minus pi's, and then I just wrote these where they belong. I'll show you what I have here. So notice that I canceled all but one of the x minus pi's. I've got the factorials where they belong, and I wrote it as 3n minus, or plus 3, because 3 times the quantity n plus 1 is 3n plus 3. I've left myself a little bit of room, as you can see, because I know what's coming and I don't want to have to write it again. So here's what's coming, is that 3n plus 3 factorial is the same as 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial. So once you have this, this is going to cancel. And then that is equal to 0. So we've got an interesting situation here. That's equal to 0. It doesn't matter what x is. X can be any number. X can be anything. And so whenever this happens, we might say something like this, that the interval, so the interval of convergence, whatever, you can spell convergence however you like, is any number. So any number from negative infinity to positive infinity, or you could say it's the reals. So that funky looking R that looks like it's got 2 down, whoops, try again. Yeah. Anyway, it's kind of like called blackboard bold for historic reasons. But anyway, yeah, the R with the 2, here, let's do this, that better. There, that looks better. So that's the reals, all the real numbers. So you could say that. That's the interval. And one of the joyous things whenever you get something like this is that you don't have to check the endpoints. So whenever this happens, you should feel free and feel good. No need to check the endpoints. All right, so hopefully this will get you through the homework. There's still more about this that we're going to deal with, but for now, this is the general gist of what the homework's going to look like. I'm going to stop the recording if you want to come chat. Otherwise, hope you have a great weekend.